Okay, so good evening, everyone. Welcome to the NPTEL online certification course for problem solving and doubt clarification on the topic water and wastewater treatment. And we are in week 9 now. Okay, so as you all know, the course instructor is Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. Okay, so let's quickly go through the contents of week 9. So in week 9 we started with filtration, where we learned about various type of filtration, what are the different type of particles removed, okay, in filtration techniques, what is depth filtration mechanism and surface filtration mechanism. And then we learned about each of them in detail, about the depth filtration and the sand filters and the surface filtration. Then we moved into disinfection. We have seen some concepts of different disinfection in the previous lectures also, but here also again we discussed about the formation of various chloramines or disinfection byproducts. Okay, so these are the main things which we looked into in disinfection. And then we started with hardness. What is the need of water softening, and what are the various causes of hardness, and how various type of complexes and precipitates are formed during hardness. Okay, so this was all about the contents of week lectures, and we will follow the same method of solving some MCQs and some numerical type questions. And in between, we will have some subjective type problems also, because in filtration there are many problems related to head loss and all. So we will see some subjective type problems related to that also. Okay, so let's start with the first question. It says that in a water treatment plant, chlorine is used or added for disinfection. The breakpoint curve is a graphical representation of the competing oxidizing agents in the water, chlorine demand of wastewater, the dose at which free chlorine will be available in the wastewater, or the effectiveness of chlorine in killing bacteria. So you have four options: A and B, B and C, C and D, and A and D. So please tell me what does this breakpoint curve represent? Okay. C and D. Does the breakpoint chlorination tell you exactly the effectiveness of chlorine? Why do you think this will tell us the effectiveness of chlorine killing the bacteria? No, right? Because we don't know. Like, only after checking like how much bacteria is present, we will know its effectiveness. Here we are only talking about the breakpoint curve, only the breakpoint curve. So what two parameters will it give? So one is definitely the dose at which free chlorine will be available in the wastewater, because we have seen it will go up and then down. So at that particular point, after which the free chlorine will be present. So it will definitely give the dose at which the free chlorine will be available. What else? So C is definitely the correct answer. What else do you think will be correct apart from the effectiveness? Because effectiveness of the chlorine killing the bacteria will only be known if we know the initial and the final amount of bacteria that is present in the system, right? So only after doing the TCFC test or some kind of coliform test, before and after giving the chlorine dose, we will know its effectiveness or the disinfection efficiency. But here we are talking about only the breakpoint curve. So yes, as Amit has already pointed out, the chlorine demand will also be represented by this breakpoint curve. So basically the chlorine demand and the amount at which free chlorine will be available in the wastewater are the two representations that we get from this breakpoint curve. Okay, so the correct option is B and C. Okay, means B and C statement, not option, B and C statement. Right, I think it's very simple. We will move on to the next problem. it says that which chloramine is formed when the pH range is less than 4.4. Is it monochloramine, dichloramine, trichloramine, or none of the above? So if the pH is less than 4.4, which chloramine do you think will be formed? So ammonia with reacting with chlorine will form various kinds of chloramines. Okay. So any idea? Trichloramines. Okay. Any other? I think you are not so sure. Any other answer? So what is the first chloramine that is formed? Is it trichloramine or monochloramine? What is the first chloramine that is formed after the addition?
Mono.
Mono.
Mono, sir.
Okay, so as and when these chloramines are formed, the pH will start, it will go down or it will increase. So what do you think, the pH will go down or it will increase? Okay, depend on the type of chlorine uses. See, yeah, chlorine will exist in different forms at different pH. That is a separate thing. Uh, okay, but
pH will decrease.
yeah, so it will decrease and slowly from the, so basically we will have three types of chloramines: mono, di, and trichloramine. So as you know that this monochloramine will be formed somewhat in the range of pH of 7.5 to 9, like from the neutral pH around that to little basic pH, these monochloramines will be formed. And then under the conditions of more uh, like this chlorination, okay, and when the pH will go down up to 4 to 6, the dichloramines will be formed. And then further, if the pH is decreased to around 4.4, these trichloramines will be formed. Okay, so in each way, some hydrogen molecules will be removed from the ammonia and it will be replaced with the chlorine atoms. Okay, so NH2Cl, then NHCl2, and then NCl3. Right? So the correct answer is trichloramine at a pH of 4 point less than 4.4. Okay, 4 to 6, always remember it is dichloramine, and above that will be the trichloramines. Right? Next problem. In the membrane filtration, the degree of selectivity of membrane largely depends on membrane charge, porosity of membrane, TDS concentration in raw wastewater, none of the above. So here we are talking about membrane concentration, membrane filtration rather. So how would we select the membrane? Will it depend on the membrane charge or membrane porosity or membrane or TDS concentration? Any other answer than TDS concentration? Anyone else? So porosity is nothing but the volume of pores, okay, to the volume of the solids. Okay, it's nothing but, how to say, like in any filter there will be some ports through which the molecules will be allowed, either it will be allowed to pass or it will be retained. Okay, so porosity is generally the ratio of the volume of pores to the volume of the solids. Okay, so over a membrane surface, how much pores is there to the volume of the solid region will be my porosity. It is nothing but the measurement of the amount of pores that is present. If more porosity means more number of pores or gaps are there, for the molecules to pass. So basically, all the three, like membrane charge, porosity, and the TDS concentration, will govern the criteria of the selectivity of my membrane. How? Suppose uh, the influent that is coming is mostly organic. So this organic matters, let's say it's negatively charged, because most of the organics will have a negative charge in the like overall. Okay, so if I have a membrane which is also negatively charged, okay, some surface treatment I have done and it is also negatively charged, then it will repel the organic foulants. Okay, and it will reduce the membrane fouling. So in that way, choosing the membrane charge is very important based on the type of feed that is coming. This is one aspect. Then the porosity. If the porosity is more, then more and more molecules will be allowed to pass through it. If the porosity is very less, uh, it will allow selective passage of the molecules. So then porosity of membrane is also very important. Then the TDS concentration. TDS concentration comes into the picture like in the case of suppose reverse osmosis, where the dissolved solids are also being retained. Okay, so based on the concentration of our TDS, also we will choose the membranes. Okay, what pore size, what is the charge, everything we have to see. And suppose if the pore size is too less and the concentration of pollutant that is coming is too high, then we may have to give some pre-treatment also, so that there is not much loading on the membrane and the membrane integrity is preserved. Okay, if too much of organic or inorganic loading comes, then there are chances that the membrane will fail or excessive fouling will be observed. So we may have to go for some pre-treatment also. So everything will account for the selectivity of membranes, right? I hope it is clear to all of you. I'm moving forward. So here is a graph which is showing the effect of the effluent turbidity with respect to time of filtration. Okay, so just that break in the graph is just to differentiate minutes into hours. So in the starting, you can see the graph is scaled at up to 30 minutes, and then it is given for 60 to 90 hours. Okay, so that break in the graph is just to change minutes to hours. That's all. So it shows the effluent turbidity, okay, during a filtration run. And it says that observe the graph given below for filter showing relationship between the effluent turbidity and the time passed from the start of filter operation. After a duration of 90 hours, which of the following operation would you not suggest in the depth filter? Okay, so after 90 hours, whether you want to change the filter media or no, which you will not select. Okay, so whether you will not change the filter media, or we will not do the backwashing, or we will not continue the filtration, or we will not scrap off the top layer. So what do you think is the correct answer? So one answer is C. So that means we will not continue with the filtration. So as you can see, during the first 30 minutes or so, the filter ripening will happen. That means that initially when the filter is just started with the filtration, there will be a sudden increase in the effluent turbidity. Okay, the particles will be allowed to pass because the maybe the void is larger, and then as and when the most of the particles has formed, then the micro pores or the micro voids will also be filled, and then proper filtration will happen for a long period of time. Okay, then after around, here it shows that after around 80 to 90 hours, again the effluent turbidity has started rising. That means now it is time that we have to either go for some kind of backwashing to remove the clogging, or we can change the filter media itself, so that we can have a fresh set of filter media and then do effective filtration, or we can even do scraping of the top layer. So all these three are some measures that we take to remove the clogging of this filter. Okay, but the only thing which we'll definitely not do after 90 hours is the filtration, because now the effluent turbidity has increased to a certain limit which will not allow it to happen. Okay, so we will always set some turbidity limit. Like once we start observing that turbidity coming out from the effluent, we will stop the filtration. So here you can see after 90 hours, around effluent turbidity of around zero point 0.3 NTU, we have stopped the run. Okay, so that's how it should be done. So the correct answer is filtration should not be continued after 90 hours. Okay, I hope it is clear. Right, now we'll solve some numericals. So for the next four numericals, we have this set of data. So I will request you to either take a screenshot of this data or note it down in your notebook. So it says that a sand filter is to be provided in a water treatment plant that caters to a population of 1.5 lakhs. The average water demand is 135 liter per capita per day, and the rate of filtration is 12 meter cube per meter square per hour. Okay, and the other given data are porosity is 0.45, uh, coefficient of drag is 5.02, kinetic viscosity is given, depth of filter media 1 meter is given, specific gravity of filter media 2.4 is given, and the density of water is given. Okay, so this is only the data. The question is still not asked. So for the next four questions, we will have this set of data only. Right? I hope you have noted down the data or you have taken the screenshot. Now we will see the first question. So it says that if the available surface area of each filter is 35 meters square, how many filters will be required? Okay, so for this condition, if the size of a filter surface area is 35 meters square, what will be my number of filters that would be required to do the design?
So every time we have to consider the maximum demand.
Maximum demand, I think in this case you can skip it, because but actually you are right. Most of the time we will see the maximum daily demand, or but here for this question you can just do it with this average water demand. Okay. If the peak factor and all is given, then you can go for the maximum demand. Otherwise, you can use this data itself. So please try to calculate. And also, I would request that since this data is not given here in this question, but for all the sand filters, you will also consider the amount, the backwashing water. Okay, so that will also come into the picture. So consider 5% of backwashing water also extra. So the total amount of water for filtration that is required, add 5 more percent for backwashing also. So now you please try to calculate. Anyone with the answer? It's basically a direct problem. There is nothing much in that. So first we'll calculate how much water is required for filtration. Okay, based on only the average water demand. Don't go for the maximum demand. But in reality, it will be designed for the maximum daily demand. Okay, with the help of peak factor and all. Then add some water for the backwashing. Okay, like I said, 5%.
Sir, I'm getting 578 meters per day.
578. Oh, you're
Meters
getting
per day.
meters per day.
Yeah, that I have to convert to meter per second.
But how you are getting meters per day? What is this? Like 570 meter per day is what?
Okay. No, the first question is what the
You have to
approach
find
velocity.
number of filters. If the filter area
Okay.
is 35,
Okay. Sorry, I'm mistaken.
not filter area is I think 1 minute. Yeah, 35 meter square. Okay, so I will start solving this. Maybe you can check. So here, this is, wait a minute. This is question number 5. So total water demand is nothing but 135 liters, okay, into change to meter cube into 1.5 lakhs people. Okay, so we'll get around 2050 meter cube per day, or it will be around 843.57 meter cube per hour. Okay, now backwash requirement, as I told you, is suppose 5% of my total water filtered per day. Okay, 5% of total water that is being filtered per day. So my total water to be filtered with the backwashing requirement will be equal to nothing but 1.05 times of 2050, that is around 2126. Yeah, I think I made a mistake here. It should be 1 minute. Let me recalculate it. 135. Yeah, it should be 20250. 20250. So here we will get it as 21262.5 meter cube per day, or it will be 885.9375 meter cube per hour. Okay, so once we got the total filter for total water to be filtered per day, we will now total required area for filtration. Okay, so it will be nothing but the discharge divided by the area. Okay, so not area, it will be the rate of filtration, not area, it will be the rate of filtration. Okay, rate of filtration. So that is nothing but 885.9375 divided by 12 meter cube per meter square per day. Okay, so we will get the area as 73.828. 73.828 meters square. So now number of filter beds required will be 73.828 divided by one filtration area. Filter bed area is 35 meters square. So by meter square, we will roughly get around 2.109. But since it is more than 2, we will provide 3 filters. Okay, so while calculating the number of filters, it should be a round number, uh, like rounded off to the higher integer. Okay, not 2, but it will be 3 filters because more than 2 are required. So this is the answer, 3 filters. Is it clear? Very simple and direct. There is nothing much in this, right? So just we have to take this into account, backwash requirement. Okay, now the next problem. So the same thing is there. Calculate the settling velocity of the filter media particle having a mean diameter of 0.65 mm. Okay, the settling velocity is in millimeter per second. So you have to calculate the settling velocity here. The particle dia is given and every other information is also given. The specific gravity, okay, and the coefficient of drag, diameter, everything is given. So you have to just calculate the settling velocity. So please calculate and let me know. Just a direct formula, or at least just tell me the formula, which formula we will apply to calculate the settling velocity. Which formula we will apply here? Anyone? Which formula we will apply to get the settling velocity here? Can we apply Stokes law? Can we apply the Stokes law here? Because we know to calculate the settling velocity either through the Stokes law or the general equation. The Stokes law is applicable only when there is a discrete particle settling. Okay, but in filter media, it may not be discrete particle settling. So we have to go through the general equation, right? Which takes into the coefficient of drag into the picture. So with that formula directly we can calculate. Okay, so question number 6 here, the diameter is 0.65 mm. Okay, or 0.65 into 10 to the power minus 3 meter, right? So the settling velocity Vs by the general equation is nothing but root over 4 by 3 specific gravity minus 1 G into D by CD. Okay, very direct and simple formula. So 4 by 3, Sg is 2.4 minus 1, G is 9.81 into 0.65 into 10 to the power minus 3 divided by CD is 5.02. So the correct answer is 0.0487 meter per second. Okay, 0.0487 meter per second. So this is the general equation. Are you guys familiar with this equation, or this is the first time you are seeing it? Hello, is this equation familiar to all of you? Am I audible?
Yes, sir.
Yeah. So I think I have shared this equation before also while I was solving a problem related to settling velocity, where we first check the settling velocity by considering it to be a discrete settling and then applied the Stokes law. Then we checked the Reynolds number. If the Reynolds number is less than 1, then we said that our assumption is correct. And if it is not less than 1, we calculated the coefficient of drag based on the Reynolds number. Okay, and then applied the general equation. Okay, and then we did it for 2 3 times, and when we are getting consistent answer, that time we stopped and said that this is the settling velocity. So that's what you have to do when we don't know what type of settling is being happening. So, but in this case, we know that discrete settling will definitely not happen. So that's why we just use the general equation directly. And this CD is also known. In that question, CD was not known initially. We calculated with the help of Reynolds number. Okay. And the CD will also change with respect to the type of flow. For laminar flow, it is I think 24 by RE. For transitional flow, it is different. Some other formula is there. And for turbulent flow, it is around 0.34, I think. So I have given all this data also, I think, in the previous class. So please check that again. Okay. Okay, so 48.7 mm per second. So I told you the answer in meter per second. It is in asked in millimeter per second, so it will be 48.7. Next question. If the design allows the filtered water for storage to meet backwashing requirements and the filter bed is required to expand by 0.46 meter, the required backwash velocity is. Okay, so backwashing is happening. So during backwashing, you know that the filter particles will expand and it is expanding up to 0.46 meter. So now you have to tell us the required backwash velocity, right? So any idea which equation will be used here? What is it called? What is the name of this equation? Any idea? Okay, let's see how to solve to get the backwash velocity if the expanded depth is given. So here again, we know that the depth of filter was given as 1 meter, right? And the porosity is given as 0.45. So this is the initial, like before backwashing. After backwashing, the depth expanded to 1 plus 0.46. So it is 1.46 meter. Okay. So now we have to find out the porosity at expanded depth. So what is the porosity? So porosity of expanded bed is given by simple formula 1 minus expanded depth porosity into depth expanded depth is equal to 1 minus normal porosity into normal depth. Okay, very simple. So 1 minus that into 1.46 is equal to 1 minus 0.45 into 1. So you'll get the expanded porosity as 0.623. So once we know the expanded porosity, to calculate the uh, backwash velocity, we have to find out the Reynolds number. So because in the equation Reynolds number is there, so Reynolds number RE is nothing but settling velocity into D by mu. Okay, so we have all this. So in the previous problem, we have calculated the settling velocity. The diameter is known in from the previous problem. So all these problems are connected. So that's why we know all this information into 0.1.004 minus 10 to the power minus 6. So RE will be around 31.528. Okay, so Reynolds number we got. Now, as per Richardson Zaki equation. Okay, so this is the equation we will use to find out the backwash velocity, and the equation is expanded velocity equal to backwash velocity by settling velocity to the power 0.2247 RE to the power 0.1. So a little complex formula. Okay, so please remember this. So once you put all the values, so solving for VB, we will get backwash velocity as 0.01096, okay, meter per second. So this will be my backwash velocity. So this equation you have to remember. So this is called a Richardson-Zaki equation. Is it clear? It's very simple. First, we will calculate the expanded porosity, then the Reynolds number, and by using this, we will use this formula. Okay, very simple. Now, we'll go to the next problem. I think this is understood. Okay, so same thing is given here. So again, in mm per second only they are asking, so 10.96. The head loss in the filter before backwashing is. So what is the head loss they are asking? Okay, so again a direct formula will be there. So head loss in this case, question number 8. So head loss is given by HL is equal to rho W. I think it is rho S, not rho W, rho S, rho S minus rho W into 1 minus porosity into D by again rho W. So it is nothing but the specific gravity minus 1 into 1 minus porosity into D. So specific gravity is 2.4 minus 1 into 1 minus porosity is 0.45 and depth is again 1. So it will be around 0.77. So this is the head loss. Okay. So all these 4 questions are connected to each other. So in the first problem, we saw how to calculate the number of filter beds, okay, based on the amount of filtration water required divided by the filtration rate. Then we calculated the settling velocity with the general equation with the help of the diameter of the particle and the drag coefficient. Then we calculated the expanded porosity followed by the Reynolds number to get the backwash velocity using the Richardson-Zaki equation. And at last, we also calculated the head loss in the system before the backwashing. So all these 4 problems will help us designing a complete filter bed. Okay. So all these informations are required to design the filter. Right. We'll move ahead. So same thing. Okay. Again, a very small numerical, though there are too much of data is given, but the actual solution is very small. Consider the following data of membrane module. A membrane module comprised of several tubular membranes and has an effective surface area of 12 meters square. The membrane system is operated in cross flow under a constant flux to yield 1700 liter per hour. The temperature is 20 degrees Celsius. Each tubular membrane is 2 meter long and is operated in outside in regime. Assume dynamic viscosity of water as this. If the tubes have an outer diameter of 3 centimeter, then the number of tubes in each tubular membrane units are. Okay, so we have to find out the number of tubes. So are you able to understand the problem? Can you visualize it, how these tubular membranes will look like? Or shall I explain? Any idea? Okay. Okay, I'll explain. So, so, so tubular membranes are nothing but in the shape of a cylinder. Okay. So suppose this is a cylinder. Okay, so this type of membranes will be there. So what will happen? Water from the outside will go in the inside. In outside in regime, it says outside in regime. That means water from the outside will go through the walls of this membrane and go inside, and from the inside it will be connected to some system or tank to get the permeate. Okay, the permeate will be going through the tubular membranes. Now one tubular is like one tubular membrane module will have thousands or hundreds of tubes like this. Okay, so it comes like a setup, something like this. Suppose this is the module, and inside this, so many this small tubes will be there. These are very thin. So many thin tubes will be there inside. Okay, so water will be coming like this. Okay, and then inside the tube it will go like this, and from there it will be coming out as permeate. So now are you able to understand? Okay, it is through the outside of the wall. Now it is saying that the total area, the total area of the membrane module is 12 meters square. Okay, and one tube is around 2 meter long and it has a 3 centimeter dia. So how many tubes are required? So now tell me, very simple and direct. How many tubes are required? Please calculate and tell me the answer. No, 3 is not the correct answer. See, the diameter is 3 centimeter. Okay, just yes, definitely. Definitely you have to convert. Otherwise, how will you solve? Dia is 3 centimeter and it is 12 meter long. And total area is 12 meter square. So how many tubes? It's simple mathematics. No, 200 is also not the correct answer. See, I always remember that it's a tube. It's a cylindrical structure. Okay, don't think it as a rectangle or cuboid or square shape. Nothing. It's a cylindrical structure. So, what is the area of one tube? Can someone tell me what is the area of one tube? I would request you to answer. Please tell me what is the area of one tube, rather the surface area. What is the surface area of a cylinder? Anyone? What is the surface area of a cylinder? Pi dl. So pi into 0.03. Okay, surface area, I am not considering the top and bottom. Okay, so yeah, so it will be pi into d into L. So just neglect the top and bottom surface because water has to pass through it. So we'll not consider that surface area. Into L is 2 meter. Okay, so something you will get. So number of tubes will be total area, that is 12 divided by pi d L. So it will be around 66.66. So roughly around 64 tubes will be required. Is it clear? Very simple. Just you have to know the surface area because it's a cylindrical. Okay, so cylindrical. So now one thing you have to remember, here the flow is outside in. Okay, from outside to in. So here you have to take the outer diameter. Okay, now suppose in the question it is given that flow is inside out. Flow is inside out means from out, inside to outside is going. So here you have to take the internal diameter. Okay, since these are very small tubes, the difference between the inside diameter and the outside diameter will be very less, but still there will be some difference. Okay, so you have to see whether it's an outside in regime or it's an inside out regime. So outside in regime, you have to take the outside diameter. For inside out regime, you have to take the internal diameter. So this is the small difference you have to make. In question, both the diameters may be given and the regime will be told. So you have to be very careful while calculating the number of tubes based on that. Okay, and there is one more thing. There are two things in this question. It is given as cross flow filtration. Okay, so there are two types of filtration. One will be cross flow filtration, and another is dead end filtration. Okay, so in cross flow filtration, what happens? Suppose this is my membrane module, and this is a membrane. Okay, that's how we will represent a membrane. So schematically, this is how we will represent a membrane. So suppose water is coming, this is the feed water. Okay, this water will go parallelly over the surface of the membrane. Okay, it will go parallelly over the surface of the membrane. Some will pass through and come out as permeate, and rest of the water will go out as concentrate or reject, we will say. So this is called as cross flow filtration, where the if this is the membrane, the flow will happen parallelly. The flow will happen parallelly. Some part will be coming out as permeate, rest will be going out as reject. So this is called as cross flow filtration. Another is dead end filtration. So in this, what will happen? This is the membrane module. The membrane will be in the bottom. Okay, and water will be coming perpendicular, perpendicular to the membrane. Okay, perpendicular to membrane. So here everything will come out as permeate. So there is, so here concentrate or reject will not be there. There will be no concentrate or reject. Everything will be coming out as permeate. And this is the feed. So you understood the question here? So mostly in this tubular type of membranes, suppose this is my tube, this is the feed water. So it's a cross flow filtration. Feed water is going like this. Okay. Some part will go as reject and some part will come as permeate into the tubes, and then from here it will come out. So these both are my permeate. See here, efficiency, we can't say directly which one will be more efficient. See, if you are sending the feed perpendicularly, okay, so what will happen, more and more particles are able to getting formed, accumulated here. Okay, so the fouling will be more in this. Fouling will be more in this. Whereas in cross flow, since it is going parallelly, the fouling or the settling of particles or the accumulation of particles over the membrane will be lesser. Okay, so
Excuse me,
you,
sir.
yeah,
But in cross flow design, water consumption more.
yeah, water consumption will be more definitely. But here the in cross flow filtration, the energy requirement will be also lesser, because if we are seeing the overall sustainability of this membrane modules or whatever, then dead end filtrations in the clogging will be very frequent. More and more energy will be required to get the permeate. Okay, maybe the
Yeah.
total amount of water required will be less because everything we will be getting as permeate. Okay, but the amount of energy we are putting it will be more over a period of time. Whereas in the cross flow, maybe some extra water we have to provide, or we can recycle the reject or the concentrate. Okay, we can do again, this recycling can be done. Okay,
Uh,
but
in which field cross flow and dead end is used?
which
Which
field
water treatment type?
See, I would say it would depend on the type of contaminant. Okay, I'm not sure field, because nowadays to get the energy savings, we are going more into cross flow filtration, and all these tubular modules are run mostly in cross flow filtration. Okay, if the
Actually, I want to know at what water parameters we can decide the cross flow is better or dead end is better for the treatment.
okay, I would say if the particles or the pollutants, if there are bigger in size and all, then this dead end filtration will get frequently choked or clogged. So in that way, cross-flow filtration will be better. But if in my filtration module the particle size and the pollutants
Better.
are lesser, then dead end will be better.
Yeah, yeah. Okay. It means suppose we are using surface water,
Ha.
then cross flow is good.
I am not
Because
sure like
surface
which
water is
will
more
be.
turbidity, na.
Ha.
Suppose you are using groundwater.
Ground. Yes.
Uh, what I am saying, surface water, it means river water, na?
Yeah. Surface water is river water. Yes.
Yeah, yeah. Surface water in river water, it has more turbidity, and groundwater
Yeah.
not more turbidity.
Not more
Then
turbidity.
dead end is better.
Then dead end is better for the groundwater. Yeah.
Yes, yes. Okay, sir.
Okay, but I am not so sure like whether on just based on turbidity we will decide. We have to also see energy into the consideration. Okay, energy aspects also we have to see, and
One more
the
question.
type of membranes also, like what is the pore size of the membranes. Okay, with respect to the
Yeah,
pollutant, that is also critical here. Because I think in more like if we have suppose a ceramic membrane and all, so there even after going to high energy like too much of pressure also it is fine, it will sustain. But but if the membranes are organic in nature, they won't be able to sustain that much high pressure. Okay, so in that case you have to go for cross flow filtration on B. So based on the type of membranes that you are using also, it will govern the type of filtration method you are using.
okay, okay.
Because most of the time if you have any ceramic membranes or metal membranes, they will easily can take the dead end filtration mode as they can sustain higher pressures,
Yeah,
right?
okay.
So many things are there. So every parameter we have to take into consideration and then decide on the filtration mode. Okay.
Okay, sir. Thank you.
Yeah. Right, just a minute. Okay, so 64 is the correct answer for this. And moving forward. Okay, yeah, some more subjective type problems are there, but I think we will first solve the MCQ type and then come back to the subjective type. So I will just go to the MCQ type. Yeah. So this is a question based on the membrane filtration, cross-flow membrane filtration rather. So it says that calculate the percentage recovery and TDS rejection for a reverse osmosis unit with the following data. So we have the feed water flow rate, we have the retentate flow rate, the TDS in the feed water and the TDS in the permeate. So we have to calculate the percentage recovery and the TDS rejection. Okay. So I will explain this. So just make a note of the parameters. I will show you how we can show this schematically. So suppose this is my membrane module. This is how we will show the membrane module. And this is my membrane, cross flow membrane. So this is the feed water that is coming. So the discharge of feed is around 2300 meter cube per day. Okay. And the concentration on the feed of TDS is around 800 milligram per liter. Now some part is going as retentate. So the flow of the retentate is around 600 meter cube per day. And again, some part will come as permeate. Okay, some part will come as permeate. So we don't know what is my permeate. So can you tell me what will be my permeate discharge? What will be my permeate discharge? Anyone?
So show the question again.
No, everything is there in this diagram itself. So feed discharge is 2300, retentate discharge is 600. So what will be my permeate discharge?
600 milligram per liter.
See, if the water is, so around 2300 water is coming and 600 goes into the retentate. So the rest of the water has to go somewhere, right? It will be coming out as permeate only. So what will be my permeate discharge? No idea? Anyone? See, simple. The water, 2300 meter cube per day of water is going into the system. 600 is coming out as retentate. Then the rest of water will be permeate, right? So it will be nothing but 2300 minus 600. It will be 1700 meter cube per day. Did you understand? Very simple. There is nothing much.
Sir, feed
Yeah.
flow is MQ per day, na? And
Huh.
this is 600 milligram per liter.
Yeah. No, it is,
So,
everything is
I
meter
am
cube per day
confused.
only.
And this is a milligram per liter.
Where it is milligram per liter? See,
Yes, yes.
everything is meter cube per day. Milligram per liter is the concentration of feed. I am not talking about concentration here. We are not just now talking about only the discharge. Okay, 2300 meter cube per day of discharge is coming into the feed. 600 meter cube per day is going as retentate. Then what will be my permeate flow rate? It will be 2300 minus 600. No, 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 there is no error. There will be no error. Okay, so in any filtration, the water has to go somewhere. If it is coming through the feed, okay, and some part is coming out as retention, then the rest will be only permeate. There like until and unless some evaporation or some chemical reaction is happening, there is nothing that the water will. There is nowhere the water will go. Okay, so here the first question was the percentage recovery. So percentage recovery is nothing but the ratio of the permeate to the ratio of the feed. Okay, so it will be 1700 by 2300 into 100 equal to 73.9%. Okay, now the next question says, next that thing that is asked is the TDS rejection. What is my TDS rejection? So the feed concentration was 800 meter cube per liter, well, 800 milligram per liter, and the concentration of permeate, okay, is 80 milligram per liter. Okay, and the concentration of permeate is 80 milligram per liter. What will be my rejection ratio? What will be my rejection ratio? So my rejection, TDS rejection will be nothing but 1 minus Cp by Cf into 100. So it will be 1 minus 80 by 800 into 100. So it will be around 90%. Okay, so my rejection, so 90% of the TDS is being getting rejected. So you can see from 800 it has become 80. So 90% has been removed. Now all these parameter, now you tell me what will be the concentration of the reject or retentate. Can someone tell me what will be my concentration of the reject or retentate? Every parameter is given here. So now tell me. Though it is not asked in the question, but I am asking here, what will be my concentration of reject? 520. How are you getting 520? Can you tell me how? Yeah,
Oh, oh, sorry, rejection. Sorry. Mistake. Sorry.
yeah. Please recalculate it. Others also please try. What will be the concentration of my reject? 1650. How did you get it?
Sir, permeate 600. 600 minus 80. Remaining 520.
600
I
minus 80. No, 600 is the discharge and CP is the pollutant concentration. It is not right.
It's a simple. Sorry, sir.
What law will be used here? Can someone tell me? What is the law that we are going to use to calculate the concentration of the reject? Anyone? Because it is not straightforward. It is not simple subtraction. What we did for calculating the percentage recovery. It is not simple subtraction. We have discussed this in some other way. We have discussed this law, but in some other way. Do you remember like the question where we have one river flowing and then a wastewater stream is coming and mixing into the river? We knew the discharge of the wastewater and the concentration of the wastewater and the discharge of the river and the concentration of the river, and then we tried to calculate the discharge of the mixed condition and the concentration of the mixed flow. Don't you think it is somewhat similar, both the things? So what law was conserved here? Do you remember?
Mass balance.
Yeah, so definitely you have to conserve the mass. What mass? The mass of the pollutant. Okay, so in throughout the system, again I will just draw it. So what is happening? There is some flow rate, there is some concentration. Some part is coming out as retentate as flow rate with some concentration, and the rest of the part is coming out as permeate with some concentration. Now if we see the total mass of pollutant, what is mass? What is the mass per day of the pollutant that is coming in? That is nothing but the discharge into the concentration. That much mass of pollutant per day is coming into the system. So let's say discharge is in meter cube per day into concentration is in some milligram per liter or milligram per meter cube I can write. So this meter will cancel. We'll get milligram per day. Okay, so that much mass is coming in one day. Okay, so this mass will not change throughout the system. This will remain conserved. So what we will do? So this mass per day is conserved. So we can say QF into CF plus, okay, QR into CR is equal to QP into CP. Can we write it like this? Can we write it like this? Is this right? Or there is some mistake? The total mass is conserved. Now tell me whether this equation is right or wrong. I would say this equation is wrong.
Sir, QRCR should be on the other side.
Yes. Not QRCR should be taken into the other side and added with the, because this is the total mass that is coming into the system and it is segregating into this and this. So it should be QFCF will be equal to QRCR plus QP into CP. So this is my correct answer. This stream is segregating into two, whereas in the river system, two streams are segregating into one. Okay, so this is the difference. Here, the segregation is different. So now QF, we know QF is 2300 and CF is around 800. QR, we know QR is around 600. CR, we have to find out, we don't know. Plus QP is around 1700 and CP is 80. Now tell me what is CR. Calculate and tell me what is CR. You will get to know something interesting. So what would be the CR here? That is the reject concentration. Please tell me the answer. First, what is the answer?
Is it 2840, sir?
Yes, it is 2840 milligram per liter. So you see, the feed that was coming was 800 milligram per liter. Okay, the permeate that we are getting was 80 milligram per liter. Okay, whereas the retentate is around 2840 milligram per liter. So we can see that whenever we have a reject or retentate, it is highly concentrated. That's why we say that whenever we are operating an RO and all, whatever water we are getting as reject, it is very highly concentrated. That's why we can see here the concentration is much higher than the feed or the permeate, because the discharge is very low. The volume per day is very low. Okay, out of the total mass, only 80 milligram per liter is going in permeate. So everything will go into the reject with a very small discharge. Okay, so that's why it is highly concentrated. Okay, so now you may be able to understand why RO rejects are very much highly concentrated. Okay, so this is the reason. And then there is a whole like separate processing to treat this reject. That's why in most of the drinking water system, the RO putting the RO system is very expensive, because there is a lot of reject that is coming out which is highly concentrated, and we also have to then treat it again. Okay, so again energy and investment cost again increases. So that's why though RO is very good, the permeate quality that we get is very good, but then again the post treatment investment or energy requirement is too high. Okay, and the kind of maintenance and operation that is required is very large. Okay, like skilled maintenance and labor is required for that. So that is the problem with RO systems. Okay, next I'll go to question number, I think, 20. I think this is also very simple. Let's try question number 28. Uh, yeah, this is an interesting question. Okay, not much values are given, but if you know the concepts, we can solve this problem. Yes, Jyoti, you are saying something?
No, sir, no, sorry.
Okay. It says that a filter is backwashed at 50 meter per hours. Okay, so backwash velocity is given at 15 degrees Celsius. Determine whether a 0.1 mm diameter particle of sand will be washed from the filter. Okay, so we have been given the backwash velocity only, and we have to check whether a particle of diameter 0.1 mm will be retained or washed away from the filter. Okay, not much values are given. Okay, so everything, like we have to consider the general things like the density of water or density of solids. We will just take it as general things and then try to solve the problem. Okay, I will show you. So just try to understand, there is one particle, backwashing is being done. Okay, the diameter of the particle is known and the backwashing velocity is known. Only these two things are known. We have to know whether it will be backwashed or not. So just I am asking you, what do you think? What are the various forces that will act on a particle during backwashing? You tell me. What are the forces that will be acting on any particle during backwashing? Any idea? So forget about this question. Just say that there is a round shaped particle, okay, and it is inside some water system, So what are the forces that will be acting on the particle? Can you tell me? This is filled with water. What are the forces? Viscous and inertial. Okay, viscosity. Like try to think very general things. Why you are making it complicated? Very basic forces. What are the very basic forces that are viscous is okay.
Gravity.
Gravity. One is definitely the gravitational force. Fg I am writing. What else? So it will be acting downwards, right? What else?
Buoyancy.
Buoyancy. So buoyancy, it will be acting in the upward direction, VB. I will write buoyancy. What else? Suppose the particle is moving, then what else? So maybe some kind of drag. Okay, suppose uh, I am assuming that the particle is flowing in the downward direction. Okay, so drag force will be upward. So suppose some drag force FD. So these are the three basic forces that will be applied on the particle. So, so when do you think the particle will start, like the particle will be washed out? When do you think the particle will be washed out from the system? At what condition?
When drag force is more than the gravity.
Yeah, so not only drag force, the drag plus the buoyancy force will be overcoming my gravity force. Okay, if my upward force is more than the downward force, then the particle will be washed away from the system. So that is the only thing which we have to check. So let's check now. So first, let us calculate the gravitational force. Okay, so how do we get the gravitational force? It is nothing but the density of the particle into the volume of the particle into g. Okay, that's all. That's all. So what is the density of the particle? Suppose it's a sand particle. So we will consider the specific gravity to be around 2.65. So this is the general specific gravity of any sand particle or anything. So the density will be 2650 kg per meter cube. And what will be the volume of the particle? We know the diameter. So pi by 6 r cube. Okay, so pi by 6 into, I think what, point 0.1 was the diameter or 1 minute. Okay, diameter pi by 6 d cube. So zero point 0.1 into 10 to the power minus 3. Okay, cube, and then g 9.81. Okay, so we'll get the gravitational forces 1.36 into 10 to the power minus 8 Newton. So this is my gravitational force. Now buoyant force, or the force of buoyancy. So FB. So this will also will be equal to, so instead of particle density, we will take water density. So rho W, rest is same, Vp into G. So this will be, so rho W will take it as 999 at 15 degrees Celsius. So 999 into pi by 6 into 0.1 into 10 to the power minus 3 cube into 9.81. So it will be around 5.13 into 10 to the power minus 9. Now to, okay, so now we will try to calculate the drag force. Okay, so drag force is given by Fd, which is nothing but Cd into rho W, okay, into the area that is exposed to drag, right, into the settling velocity square by 2. Okay, so this is the drag force. So Cd is generally around 19.7 into 999 into area of the particle will be pi by 4 into 0.91 into 10 to the power minus 3 square. Okay, so everything will be okay. Here I have written it, so it will be pi by 6, yeah, square. Now settling velocity, or the velocity of the backwash, is given as 50. So I will change into 3600 to meter per second divided square. So we'll get the drag force as around 1.49 into 10 to the power minus 8 Newton. Okay, so now the net force acting. So the net force acting will be equal to the gravitational force minus the buoyant force minus the drag force. So it will be around, so 1.36 into 10 to the power minus 8 minus 5.13 into 10 to the power minus 9 minus 1.49 into 10 to the power minus 8. So we'll get it as minus 6.43 into 10 to the power minus 9. So this negative sign indicates that the net force is acting upwards. So since the net force is acting upwards, we can say that the particle will be flushed away. Okay. So since the net force is acting vertically upwards, we can say that the particles will be flushed away. Right? So did you understand the problem? Okay, so I don't think this type of problem will come in the examination, but just to clear your fundamentals, I have kept this. So if this type of problems comes also, all these parameter values will be given to you. Nothing like no assumptions have to be made. Okay, because everyone has to get consistent result. So the parameters will be given. But this is how you have to solve. First the gravitational force, then the buoyant force, then the drag force, then find out the net force acting. And if it is upwards, that means the particle will be flushed away. Right? I hope this is clear to all of you. Okay, now we will just quickly solve some multiple choice that is left, I think. Yeah, it says that dialysis in our kidneys is concentration driven separation process, thermally driven separation process, pressure driven separation process, or none of the above. What do you think? Anyone knows about dialysis? Have you heard about this? So it is definitely concentration driven. So I think nothing much to discuss about it. Okay. Yeah. Yeah. Right, Amit. It is just to make the blood clean. So based on the concentration, okay, the separation happens. So it's a concentration driven. If the raw water turbidity is less than 10 NTU, then which of the following treatment trail will be favorable? So you might have seen for various types of suspended solids concentration present, we will follow some kind of treatment trail. So when the turbidity is less than 10 NTU, what will be my treatment trail? Like which of them will not be required? Simple. Which of the treatments will not be required? B. Yeah. So that is true. First coagulation, flocculation. Then we need not go for any sedimentation. Okay. It can be directly followed by the filtration, then disinfection. Okay. Just this order is correct. Only we have to check whether sedimentation is required or not. So very direct. If the sand media has uniformly distributed particle size, then it is best suited for which of the following? Rapid sand, slow sand, particle size distribution does not affect rate of filtration, or none of the above. So we have uniformly distributed particle size. Why do you think it's a slow sand filter? The correct answer is rapid sand filter. So always remember, if it's a uniformly distributed particles, then the type of voids will be comparatively larger. Okay, so the rate of filtration will be larger. But if it is like the particle size is having all types of particles, like starting from the bigger particles to the most smaller particles, then the types of voids will be much lesser, and it will be good for a slow sand filter, not a rapid sand filter. Okay, but if it is uniform size, then the particle voids will be a little larger, because all the voids will not be filled, because every particle is of the same size. So then we can only use it for a rapid sand filter. Okay, again this same problem which we saw. uh, okay, last question. The separation limit for a membrane is determined by the lowest dash that can be separated. So separation limit is defined as per molecular weight, ionic weight, or mass.
सर क्वेश्चन को एक बार समझा दीजिए.
No, it is saying that the limit, like what is the least size that can be removed from the membrane, is based on the molecular weight or ionic weight or mass. Like generally, this is how we will define a membrane, that the membrane can only separate up to this or this size. So what is that parameter? So it is definitely the molecular weight, because based on the molecular weight, or we define it as an kilodaltons. So based on the kilodalton, uh, I think depend on the type of, yeah, see, type of membrane will be different. Okay, because many a times it is not directly possible to calculate the pore size of the membranes. Okay, and the membrane pore size will not be uniform throughout the membrane also. While casting the membrane, maybe the membrane pore size is not similar throughout the membrane. So in that cases, we define the membrane based on the least molecular weight that it can separate out. Okay, so in terms of molecular weight or in kilodaltons, we will define it. So that is the major parameter. Okay, the same problem is there. Okay, so I think, yeah, that's all for today's class. So we'll meet again on 1st April, Tuesday, 7 to 9 p.m. And if you have any doubts or clarifications, you can mail me at saha19akash@gmail.com. Okay. If you have no more doubts or discussions, you can leave the session.
सर वन क्वेश्चन रिपीट सर.
Yeah.
वो क्वेश्चन था ना, QF इंटू CF इज इक्वल टू QR CR प्लस QP CP.
Yes, yes, yes.
उसमें थोड़ा एक्सप्लेन कर दीजिए सर. QF CF का क्या क्या है?
हाँ, एक सेकंड मैं बता देता हूँ. Okay. See, suppose
No, only tell me. QF is the feed flow,
feed
and
concentration.
CF is the concentration of feed,
CF is the concentration of feed. QF
and
is the
QR is
QR is
QR
discharge of the retentate or reject.
discharge of reject, and CR is
Concentration of the reject.
अच्छा discharge of reject means नहीं समझा.
See, discharge means, that is different. See, discharge means how much volume of water is coming per day. Okay, so suppose some 100 meter cube per day is coming. So from that, some is going into reject. Suppose 30 meter cube per day is going as reject, and the rest is coming as permeate, 70 meter cube per day. So these are all discharge. So this is QF, this is QR, this is QP.
And the
And
QP is
QP is permeate
half
discharge,
permeate of discharge, and CP is the
concentration
concentration
of
of
permeate, and
permeate. Correct, correct.
CR is the concentration of reject, and
Oh,
CF
I
is the
know.
concentration of feed.
Okay,
Okay.
okay. Thank you, sir. Thank you.
Yeah. Okay, so that's all from my side. If you don't have any more doubts, you can leave the session. Thank you. Yeah, Amit, you want to say something?
सर एक बार मैंने प्रीवियस लेक्चर में क्वेश्चन पूछा था फॉर्म के रिगार्डिंग
फॉर्म के रिगार्डिंग, हाँ, क्या क्या क्वेश्चन था?
वैसे तो सर कॉन्सेप्ट तो ये है कि डिफरेंट टाइप्स ऑफ फॉर्म्स बताते हैं कि बैक्टीरिया कौन सा है राइट
हाँ, या
मैंने पूछा था फॉर्म्स को क्वालिटी से रिलेट करने के लिए
Yeah, see, foams, there can be two major reasons. Either there is too much of oil, grease, and surfactants are present, then foams will be formed, or this particular type of this, what to say, this filamentous bacteria or something is there. That type of bacteria is mostly present. Then again, this foam will be formed.
सर व्हाट आई ऑब्जर्व मैनी टाइम्स अगर हमारे वाटर में ऑर्गेनिक वेस्ट है तो फॉर्म नहीं होते लेकिन ऑर्गेनिक वेस्ट कम होता है तो बहुत सारे फॉर्म आ जाते हैं एरिएशन टाइम पर
See, organic waste, not only organic waste, I am saying that if more and more surfactants like detergent kind of thing or some oil and grease, these kind of things are present, which are not like easily degradable by the biological actions, then more foams will be formed. Okay, so you are correct in some to some extent that if lesser organic particle and more of these surfactants and all are present, then foaming will be more. But if more and more organic, easily biodegradable matter is present, then the foaming will be less, which the bacteria can directly mineralize into the carbon dioxide and water. Okay, but this oil, grease, and surfactants are little difficult for the bacteria to solubilize and then mineralize. So that is the problem. Are you able to understand?
यस सर
Okay.
सर एक और क्वेश्चन पूछो इट कैन बी सिली माइट बी
हाँ.
लाइक मेरे पास इनलेट वाटर है जिसकी बीओडी पहले से ही बहुत कम है
Okay.
मेरे को उसको ट्रीट करना है तो वो क्या वो ट्रीट होगा और उसमें ऑर्गेनिक वेस्ट
Sorry. The organic waste is less.
हाँ जी सर मेरे पास मान लीजिए एक सैंपल है उसमें उसकी बीओडी पहले से ही बहुत कम है और
Okay.
उसमें ऑर्गेनिक वेस्ट भी नहीं है तो वो कितने लिमिट तक वो ट्रीट हो सकता है या वो ट्रीट ही नहीं होगा
You see, you have to always like the type of treatment you are providing depends on the BOD by COD ratio. Okay, if the biodegradable organic matter that is present is too low, then we will go for some other kind of uh, methods, treatments, some chemical or physicochemical techniques. You're asking that only, right?
अगर सर हम बीओडी को कंसिडरेशन में ले तो
BOD, yeah, but if BOD is already less, like to what extent you want to? You want to like go up to zero, like that you are saying. If
नो सर
no, I'm not getting your question properly, actually.
Suppose my initial BOD is around 70 to 80 milligram per liter.
Okay.
Then how much extent it will decrease?
Yeah, it won't decrease up to like very less, like up to zero. It is very difficult because some kind of concentration gradient has to be there. Okay. And yeah, if you are trying to decrease it by biological action, 70 to 80 can be decreased up to 5 to 10 milligram per liter. It won't be an
बट
issue.
मुझे पता है सर क्या लगता है कि अगर उस पे ऑर्गेनिक वेस्ट नहीं होगा तो माइक्रो ऑर्गेनिजम्स या बैक्टीरिया सस्टेन ही नहीं कर पाएंगे, उनको एनर्जी नहीं मिलेगी.
See, for that reason, yeah, you may have to store it and then increase the organic loading.
ओके सर,
Okay.
जस्ट आस्किंग.
Or maybe you can also, what you can do is like provide more recycling, okay, for the bacteria to get more microbes for like the action, for the microbial action. Like that also you can do. Right? Anything else? No, no, nothing. Whatever is given in the lecture video, that is enough. That is enough. Nothing will be asked outside for that.
बट सर बहुत सारे क्वेश्चन ऐसे भी मिले थे जो लेक्चर में नहीं थे, फिर भी उनको
Then you
सोल्व
only
करना पड़ा.
consider whatever is there in the assignments and the lectures. Nothing else. I don't think anything
लाइक
else will
सर
be.
जैसे एक क्वेश्चन आज ही आया था डायलिसिस के बारे में, वो तो लेक्चर में नहीं बताया गया
No,
था,
but
उसके बारे में तो मैं
see,
नॉलेज
these
होनी
are
चाहिए
these are common things. Dialysis is a common thing. Like people generally know.
था.
Okay. So you have
बट
to
सर
relate.
मैंने और भी क्वेश्चन ऐसे पूछे थे जो आउट ऑफ लेक्चर थे.
See, you concentrate on the type of questions which are being given as assignment, not the questions which I am teaching. I am teaching some questions maybe somewhat out of syllabus, but with the same concepts. You might not have directly read or studied that thing, but it is based on similar concept. There is nothing like out of syllabus or anything. It may be a little bit advanced. That's all. Okay, but most of the questions which I am also teaching is from the same syllabus what is being taught in the lectures. Maybe some formulas here and there, like this water demand formula. Maybe I have given some more extra one or two formulas which are not there in the lectures. Maybe you can skip those things. Okay. Otherwise, the concepts or the conceptual problems regarding this degradation, BOD, COD, all things can be asked. It is of similar concept only. Maybe you can skip some extra formulas which I have taught or I have shown in the assignment. Okay. All right then. Okay, thank you.
Roshni,